Okay, one more cellular automata. Get a share screen going. I want to talk about a percolation model of self-propagating star formation in a rotating galaxy. I kind of love this because it was first published in Science, which is like a big name journal, in 1986, and it appeared in Advanced Physics in 1990. Early days of galaxy modeling. The idea behind it was that a shock wave from a nova, which is what happens when a star dies, triggers star formation around it. The shock wave produces a density variation, mass clumps up, and it increases the probability that it will collapse into a new star. It's sort of like the game of life empty cell with three neighbors that's born. As the star ages with time, its probability of going nova increases. And I should note here, when I'm talking about a star, I'm actually talking about clusters of millions of stars, each of which have some probability. So it's sort of like the game of life living cell that dies of loneliness or overcrowding, except that its death then triggers births around it. Another issue is that galaxies experience differential motion. Now, what I mean by this has to do with the fact that galaxies rotate, and they don't rotate like a wheel, and nor do they rotate as if they were inverse square orbits. Instead, what is observed is that the tangential velocity of stars is almost uniform, varying almost not at all with distance from the center. You would expect it to be r to the 1/2 dependent if they were inverse square orbits. The reason for this is the reason we expect that there's something called dark matter out there, clouds of invisible stuff we can't see that must be there to explain this odd velocity pattern. So given that, instead of a fixed checkerboard, we have a circular grid with an arrangement that's designed in such a way that the number of cells in each layer increases linearly with distance. Circumference is 2 pi r. So here's our grid. Any cell's neighborhood consists of one to the left and to the right, two in the shell above, two in the shell below, a total of 6 neighbors. But the neighborhood changes with time due to the rotation of the different radius shells. With a uniform velocity, the angular velocity is v over r. And so as these things rotate, the neighborhood changes. So our program structure is to calculate the occurrence of novas, a probability dependent that depends on the star's age. We then trigger star formation in the current neighborhood, and then we rotate the shell so everyone has new neighbors. For fun, we'll size the stars according to age, and we'll also add the possibility of supernova for large stars. This is not actually part of the formulation, but I just added it for visual effect. So this is what our galaxy is going to end up looking like. We have these spiral arms that is characteristic of our type of galaxy, the Milky Way, and they kind of spiral in from the center, and this is what many galaxies look like. So how are we going to organize this? First of all, the first ring has 6, the second 12, the third 18, and so forth. So our total number of cells is 3 times the number of rings times the number of rings plus 1. We'll maintain all this in 2 1D arrays, cell R and cell A, with R going from 1 to the number of rings and A being its location within a ring. And this is going to produce for us a simple way to look up the location of any particular cell by its R ring and A position in the ring location. We'll define our neighborhoods at the different the different rings with A for other radius, which includes both the time, that's what's going to rotate them, and the velocity of rotation V that returns A, the value of the ring above and below our center cell that's going to be in ring R, position A within the ring. We have an array of active cell labels that keeps track of which cells are active. That is, they're able to instigate star formation in neighbors. In the initialization, we'll specify an initial number of stars, and we'll loop over random locations instantiating stars in that one-dimensional array. Properties will include the object, stars, an array that's initially null, initial lifetime, whether it's a nova object, its parent object, and possibly its name and material color. So this is the initialization. We're just going to randomly generate stars. And each pass through the coroutine updater will draw our stars, wait for an interval, advance the time t, and then test whether new stars are formed around active cells. That's the form new stars routine. Form new stars first makes a copy of the active cell and then loops through all those active cells, extracting each R and A coordinate from the cell R and cell A, and will activate cells to the left and right and in the ring above and below. And we have a little periodic boundary condition, PBC, that handles the wraparound between the A equals 0 and the A equal maximum within a particular ring. So we're creating these stars. That's the PBC function, which uses a very clever mod function to wrap around. The create star function locates the cell label from its AR coordinates, tests the probability while restricting it to stars that are not brand new, updates the active cell label array, sets its lifetime, and if not already active, instantiates a star object with all its appropriate properties. All that's left is to draw our stars, so we just go through the number of cells, where action is taken if the star's lifetime is still positive, updating its position in the moving grid, and modifying its size to reflect the amount of time left. If lifetime has reached 0, we handle the star's death, which may be as a supernova. This is a low probability event, but if it is, we'll catch its position, destroy the star, and then instantiate the supernova object. If appropriate, then we trigger star formation around the new supernova with a much higher probability, very high probability around supernova. Supernovas themselves ultimately die out, in which case we just destroy them. There's one more issue to deal with, and that's that we're instantiating lots of objects and then soon after destroying them. And this is a situation that cries out for object pooling. The idea behind object pooling is that instead of making and unmaking, instantiating and destroying, we'll instead, at the beginning, instantiate a pool of objects, set them all to be inactive, and as we need them, set them to be active, move them into place, adjusting size, color, etc. When we're done with an object, instead of destroying it, we return it to the inactive pool. One way to do this is to use the list instead of the square bracket arrays. Because it has tools like add and remove that allow us to manipulate the pool easily. In particular, when we run out of objects in the pool, we can expand the pool by very simply adding an object. We can modify this to use the much faster square bracket arrays. Uh, the, the modification is relatively simple, with the caveat that with the square bracket arrays, if we want to add one to it, we have to first make a copy, add one more, make a new array with one more item in it, and then copy them all into the new array. So this can be potentially expensive. In benchmarking this, I found that the impact on performance was relatively small, although the array pool and the list pool, at least in this case, did beat the instantiate, not by a whole lot. 14% improvement for the list, 25% for the arrays, and the arrays were about 10% better than lists. I did not get the same result every time I did this. 4 out of 5 times I did get not results that good. It's essential that the initial pool size be roughly what you're going to need, as pool growing is fairly expensive. In the case of the square bracket arrays, there's an order n traversal of the already used items to find that they've all been used up. Then an order n copy of the new temp array and a copy back. I don't know what goes on behind the scenes for the list data structure, but it's got to be something similar. One significant improvement with the Galaxy had to do with memory usage. With the instantiate version, memory usage grows continuously, whereas both of the pools plateau and remain constant, indicating even though we are destroying objects, there's some memory overhead in instantiating all those objects with materials with different colors. So let me show you what this looks like here. I have, first of all, an instantiate. So here's our instantiated Galaxy. The total number of occupiable sites is listed here. So we're running at about 30% of them, with varying numbers of active stars and supernovas. The list pool is going to look more or less exactly the same. The list pool seems to be a little slower on my computer, and the array pool that runs faster than these. There is a benchmark that will run through, I think, a minute each of the 3 different instantiate, list, and array pools, writing out information that is what I generated that picture with. Here's a situation with a lot more rings. And so its performance is quite a bit slower. It's still generating a nice looking Galaxy, and it runs for quite a bit of time. There are a couple of cases here where I just started out with a few in the center to see what would happen. And here's one called Birth of a Galaxy, which starts off with a bunch in the center, and it takes it a while, but eventually the star formation reaches out to the edge of the galaxy, and you have a fully formed 100-ring galaxy. Now, one thing that's very interesting about this is how sensitive it is to what you specify as the probability of the birth of a star. And that probability for this case is 0.18. I just want to show you 3 cases where I vary that probability only very slightly. So instead of 0.18, here's the probability of 0.17. It almost instantaneously dies out. The galaxy does not persist. If I increase it to just 0.19, the galaxy fills up, and it's almost completely filled with stars. And here's one with 0.20 that fills even more. So clearly this probability of the birth of a star, which might depend on something like the density of the galactic dust or something like that. Who knows? It's very, very sensitive to this. And in the 0.18 case, we get nice spiral arm galaxies. In the 0.20 case, we get something that might look more like a globular cluster, a spherical galaxy. So who knows what all this stuff means? And of course, the galactic modelers have gone way beyond this with N-body problems with hundreds to millions of star particles that they work with. Neil Cummins here at the physics department actually does a lot of this stuff. So I'm going to stop sharing here at this point, and I'm going to end the recording. And I think this is pretty much all I'm going to do with cellular automata, but it has been a fun ride. I'll see you all in class. Bye.